So as you already noticed, or will certainly notice, English is not my primarily language. So don't worry, I'll try to be as clear as possible. I'm here to talk to you about the Brossard Aquatic Complex, which won the second place on the low-rise structure. But first, for those who never heard of CIMA Plus, we are an employee-owned multidisciplinary consulting firm founded in the 1990. Although we don't have a strong presence in the United States, we are among the largest private consulting firm in Canada, with over 30 offices and 2,800 employees all across the country. At our main office in Montreal, our structural engineer division is mainly present in public infrastructure projects such as schools, hospitals, and aquatic complex. We specialize in concrete, steel, and wood structure. So let's get back to Brossard. The owner of the building is the city of Brossard, which is located about 15 minutes south of downtown Montreal. There were two architectural firms in the project. There were Eloise Thibodeau Architect and Prism Architecture. The engineering firm was CIMA Plus, and we worked on the structural, civil, mechanical, and electrical engineering for that project. The general contractor was EDC, and the concrete supplier was Lafarge. So, like I said, the building is located in Brossard, Quebec, in Canada. The complex includes two swimming pools, one 50 meters long competition pool with 10 swimming lanes, and as well as 3 concrete diving platforms ranging from 1 to 5 meters high. 50 meters long is Olympic size pool, so there's only a few ones in Quebec. The other pool is a smaller 25 meters recreational pool with the 5 swimming lanes, spray fountains, and a water slide. The footprint of the building is approximately 5,350 square meters, or about 58,000 square feet. And it's built over 2 stories. So the structure of the building is a mixed concrete and steel construction. The building sits on pile foundations. The lower levels and pool are constructed in reinforced concrete, and the superstructure and the roof are constructed in steel. Overall, slightly 5,000 cubic meters were poured through the project. The ground floor portion above the basement feature a two-way slab on concrete columns, while the section without basement is mainly a one-way structural slab on grade on concrete grade beams. Both pools are constructed in cast-in-place concrete supported on piles. The second story floor is composed of a one-way slab on concrete beams that allow the building's envelope to be cantilevered from the second floor to the roof. The second floor includes cast-in-place concrete stands cantilevered from the main structure, which give the impression that the stands are floating above the pool section. And finally, there's an impressive openings, which we can see in part right there, from 7 meters, from 4.5 meters on the second floor, which gives the more natural light through the skylight. So yeah, there's a lot that cantilevered on that project. The story slab presents several challenges. Like we said before, the steel roof actually stands on a 2 meters concrete cantilever. We opt for the one-way slab on beams so that the beams could help carrying the point load of the steel columns. Inside the buildings, we opt for cast-in-place stands. The stands are cantilevered over 1.3 meters to 2.2 meters, and they're sloped. So we designed the beams with the slope to match the height of the stands. Finally, on one corner of the building, that one, the envelope is set back inside the building so that the last beams is cantilevered from 5.5 meters long. So it's kind of impressive to see that the second floor is like floating over the passengers, the pedestrian space. So one of the main features of an aquatic centers and most of aquatic centers is the diving platforms. In that case, mainly the 5 meters tall diving platforms, which is kind of impressive. It's kind of huge. It was very important to get an impeccable finish. So to facilitate the placement of the concrete and obtain the most uniform finish possible, we use a 14 millimeters aggregate, and we use a textile lining in the formwork to have the smooth finish. The textile absorb a part of the concrete at the finish, so there is less imperfection on the concrete. The height and the overhang and shape of the arc of the diving platform are elements that made the design of these platforms very complex. We start our design thinking by thinking about a C shape first, and then we add an arch with is designed like there's an angular beam within the arch, and because the weight of the diving platform is offset, we design a triangular void within the arc to minimize this offset mass and minimize the efforts in the base. Yes, that is that. And one of our challenge was the deflection at the tip of the diving platform, because we have a cantilevered platform, but as well as there's a rotation on the base. So each degree of rotation you have on the base made more accent of the deflection on the tip. So any little rotation is a big impact on the deflection on the tip. So we built a 1 meter thick foundation was sitting on 4 piles to be sure as the base was as stiff as possible to minimize that rotation. And finally, we have an invert camber on the diving platform so that the initial deflection will sit at the correct height, because the diving platform needs to require the FINA specification. FINA is the Swimming International Federation. So we have deflection in concrete, but they don't allow much deflection. So we designed it so the initial deflection was as the maximum height allowed by them. So overall, it's make a kind of impressive structure. Finally, exposed concrete is showcased through the building as it was the intent of the architectural design. The concrete floor in the entrance hall and corridors features polished concrete surface, and the exposed circular columns in the entrance as well as were poured with the PVC line formwork to provide a smooth and shiny finish. The result is very beautiful, like you can see in that picture.